This one is going to talk about recoil. And an easy way to discuss recoil is thinking about some examples. So let's start there. So, examples of recoil would be like firing a cannon. Whenever you fire a cannon, the cannonball goes back. So, ball actually goes forward. And then the cannon rolls back. Another example would be, let's see, how about a firearm, shotgun? How about that? So firing a shotgun. So whenever you fire it, the bullet goes forward. And then the shotgun kicks back. This is what recoil is. It's this rollback, kickback. It's like a pushback or a bounce back, something like that. And the reason why it happens is all because of conservation of momentum. The idea that the amount of momentum before has to equal the amount of momentum after. And another way of saying this with recoil is for something to go forward, something else has to go backwards. And so that is what we are going to see in our diagram, our picture, showing us the different stages, and also in the example that we're about to do. So let's talk about what this looks like. And we'll use a cannon as an example. We have before, and then we have after. There is a boom that happens. This is whenever you fire the cannon, you fire the shotgun, whatever it is that is recoiling. So let's use our red and our blue again, just like in our collisions. So here's my cannon. And inside is a cannonball, like so. Well, initially, it's just sitting here, isn't it? All right. Well, that means our momentum here is 0. The momentum of the cannon is 0. The momentum of the cannonball is 0. They're together. They're 0. Then the boom happens. This is where a force is applied. So the gunpowder then explodes. And when it does, it provides a force on the cannon and a force on the cannonball. Those forces are equal and opposite. Therefore, the cannonball goes flying forward with a large velocity. The cannon goes backwards with a small velocity. Well, I thought we said this was conservation of momentum. So how is it conserved if this cannonball is going so fast and the cannon is going back so slowly? Well, it's because momentum is conserved. Nothing to do about specific velocities. It's the momentum. And so the momentum of the cannon, sorry, not M, gracious. The momentum of the cannon is equal to the momentum of the cannonball. Since it has to be zero, these have to be equal but opposite. Well, the cannon has a gigantic mass. I mean, you can't even pick these things up. They have to be rolled into place. The cannonball, relatively speaking, has a small mass. You can pick up a cannonball. It's pretty heavy, but it's still possible. Well, for these to have equal momentums, then if the cannon has an extremely large mass, it must have a small velocity. And if the cannonball has a very small mass, it must have a large velocity. And this is why even something like a handgun, for its size, it's pretty heavy. And it's because it has to have a very large mass so that it doesn't kick back with too much velocity for that bullet to go forward. That trade-off between mass and velocity is how it's able to keep equal total momentum. So let's do an example. All right, we're going to do the same like we did before. MVP, MVP. We have the cannon, and we have the cannonball. How do we know that this is a recoil example? Right here. With what speed did the cannon recoil? Well, the cannon has a mass of 500, which is going to be the same on both sides. The cannonball has a mass of 10, which is also the same on both sides. Well, initially, before that cannon fired, it was at rest. So if it's at rest, then that means this whole side over here, this is 0, which means this is 0. So this whole side is 0. Well, then how are these moving? Right? Afterward, how is it moving? Well, the cannonball is going 200, so that's our blue, right? This one is going 200 meters per second. Well, let's find our P. 10 times 200, well, that's 2,000, isn't it? Well, if our total momentum before is 0, then that means the total here also has to be 0. The only way for that to be the case is if the cannonball was 2,000, then the cannon has to be negative 2,000. Hence, why the cannon goes backwards. That negative means backwards. And from there, we can indeed solve for the velocity. So what makes these a little easier is the whole left side here, before it's fired, the whole left side's 0. So all you have to worry about is what's happening on that right side. And so we have 500 times V equals 2,000. So divide by 500, and we get a V. Oh, negative. Sorry. There we go. Negative 2,000. And so we get a V of negative 4 meters per second. That is how, if initially it's not going anywhere, has a total momentum of 0, that cannonball can still go flying off, is because it has a positive momentum. The cannon has a negative equal momentum. The cannon has a very large mass, and so it has a very small velocity. And so it rolls back a little while the cannonball goes flying. If you'd like to see a different approach to how to do recoil, make sure that you go into the Heier 2020 collisions video. He does recoil at the end. Or you can look at the end of the one that says old collisions. It goes through a slightly different way of looking at these problems. And so feel free to do that to see if maybe those make a little bit more sense.